Welcome to the next screencast, which will focus on chapter 9 of the Tensor book. And we are going to talk about three-dimensional Schrödinger equation, and in particular, we are going to look at the two-body problem. In the future chapters, we will start looking at application of what we're going to do today in this screencast. In particular, we are going to generalize what we've done in terms of translation and rotation for the two-body in three dimensions, what we've done in one dimension. So you will remember that, of course, rotation of the real space is something a little bit difficult to grasp in one dimension. It doesn't make much sense. So we spoke mostly about spins. Today we are going to talk about the rotation in three dimensions, and these things will come naturally as an extension of what we've done before. We are going to spend a lot of time talking about commutators today. We know the central role of commutators in quantum mechanics, and we will see that it's also true in three dimensions. Luckily, many of those commutators do cancel, get to zero as zeros between the different components, but not all of them. And this is going to come naturally during this course, during this screencast. So let's go to three dimension. Okay, so formally, we can write a state vector in three dimensions as x, y, and z. So this is explicitly describing the position x, y, and z of the state vector. Well, still remember that state vector, that ket, is all the information you can get about a given particle. But the labels we can use is x, y, and z, which there is a shorthand, which is simply the vector r. Okay, so far it's simply a notation, really. We were limited to simply a x label before. Now, we can define those as being as stemming from an eigenvalue problem. So we can introduce the operator x, y, and z, which simply return the value of x, y, and z coordinates for each of those state vectors that are written x, y, and z. So this is again very formal. This is a definition. Again, we introduce this definition. There is very little to understand here since it's merely a definition. So here we are defining again an operator through its eigenvalue problem. Of course, since these operators are Hermitian, and the eigenstates certainly constitute a complete basis that we can use. So we have a completeness relation. The completeness relation here is a little bit longer to write, but really it's simply an expansion in x, y, and z of what we've done for x, for the continuous variables x, y, and z. And then, of course, on the right-hand side of the equation there on the red box, we have the shorthand notation where we use vectors, as you have seen probably in many other courses. In addition to completeness relation, we have a good basis if we have an orthogonality relation, which simply means that if I take two state vector x, y, and z, and x prime, y prime, z prime, it's going to be 0 unless x equal to x prime, y equal to y prime, and z equal to z prime. So this is written using the Dirac delta relation that we've done. So we call about, I repeat this again, we talk about Dirac delta functions that are not exactly functions, they are more distributions. But for the sake of what we are doing here, we can consider they are functions that are sharp function at the when the argument is 0 and 0 otherwise. I know that it's not completely mathematically rigorous, but for our purpose here, that will suffice for describing what we want to describe. Okay, so we can move on and also talk about probability density. And the probability density comes directly from remembering that if I take a state psi, which is properly normalized, in other words, I know that the particle exists somewhere in space, I can introduce twice the identity operator, which is going to obtain in three dimensions. And I end up with this equation here, which you probably have seen before, which simply says that the integral over the entire space in 3 dimensions of the square of the modulus between the projection of R and psi, so that integral is equal to 1. That shows us, of course, that this little volume d3r is we look at the density of charge at that position, the density of particles, sorry, at that position for a little volume of volume dx times dy times dz. So it's a little cube of that dimension. So we have again a probability density which is given by the square of the bracket, the square modulus of the bracket. In this case, the density is in 3D, so it's per volume. Instead, what we've done in chapter 6 were per unit length, right? Because we were in 1 dimension. So if we want to get the probability, of course, we have to multiply this by a volume element, which is the d cube r. Okay, I think this is all very straightforward. Now we can move, of course, just like we did in chapter 6, we can also expand this to 3 dimension. And we are going to talk about 3-dimensional translation operator. These are just defined here on the red box on this slide. The first translation is along the x-axis, the second the y-axis, and the third to the z-axis. And the effect on the eigenstate of the R operator is to translate each position by x, by ax, ay, or az. So of course we can write this translation in general for a vector A, which has component ax, ay, az, and of course we can use the compact notation. So this is again a definition how a translation operator in 3D operates on a state vector R, and what it does is actually translate the whole thing by a vector A. That's what it does. We also remember that because T will be unitary, and the reason why it's unitary is for the same reasons that we already discussed a number of times. It's because the total probability should not be modified by a simple translation, so it has to be a unitary transformation. We can therefore introduce generators of the translation. And just the same way as we did in that 1 dimension, we can introduce 3 generators for translation in x, in y, and in z. And so we introduce px, py, pz, which are going to be the linear moment, the component of the linear momentum vector in 3 dimensions. So far so good. I mean, we are essentially expanding what we've done in 1D, and we have been careful so far. We have not really taken any risk in combining operators and trying to assume that operators commute or do not commute. We have not done any of that. We just laid out the foundation of what we want to do next. So of course what we to do next is to start to calculate those commutation. So first of all, we can establish that the translation in 2 different directions will commute. So what it means is that if you translate your vector along x followed by a translation along y, is the same thing as translating along y and then translating along x. So that part is fairly straightforward to understand, and in fact we can go beyond this by seeing what's the effect of that commutation. What will be the effect on the commutation between px and py. And in fact, if you use Taylor's expansion of the exponential, because remember the translation operators, we've seen on the previous slide that they can be expressed as complex exponential. If we do that for x and for y, we find in fact that px and py do commute. So the fact that the translation operators, along x and y commute is translated also for the generators of those translations. So that's very interesting, because it says that the different component of linear momentum commute, which is a big help, right? It's a big help because, and we'll see that later, we will be able to use eigenstate that are common eigenstate of px and py to find the eigenstate of some operators later, right? The zero commutator is always a very useful attribute to get in order to solve complicated eigenvalue problem. So the consequence, of course, and this is a very important consequence, the first equality comes simply by the introduction of the generator, that the translation along a vector A is equal to the application of a translation along Z, along Y, along X, the fact that the translation commute and the different Px, Py commute, we can write the last equality. Do not be fooled. This last equality is only true because the different components of P commute. This is something that we've already discussed before, but we cannot write the last equality in the red box if we could not write it if Px and Py did not commute, and of course Px, Pz, Py, Pz did not commute. Okay, so the thing is that all in all, at the end of the day, what we see is that the translation operator can be written as a complex exponential of a certain vector P, which has component Px, Py, Pz, and a vector A, which is the vector of translation. Okay, now what we've learned before is that in one dimension, the position operator and the linear momentum operator along that direction, they do not commute. In fact, they is equal to IH bar, which of course yield the uncertainty principle between delta x and delta px. It's clear that we have the same relationship along the y direction, and we have a same relationship along the z direction. Now, of course, the natural question we can ask ourselves is, what about the other different directions? In other words, what would be, for instance, the commutator between the operator x and the operator py, or any other combination? So let's try to see this. So this here is, I take a general state psi, and I first apply the operator y, so it's going to return the position, and then I apply the translation along ax. The question is that equivalent to do the way around, first translating and then the position? It would seem from intuition, from classical physics, that it would certainly be the same, since I only get the position along y and then I translate along x. That should not make any difference. But let's show this, because this is a good exercise to remember to use the identity operator. So here I introduce the identity operator in 3 dimensions. I hope you recognize it. It's the part that starts with the 3 integrals. The advantage of this, of course, is because of the basis I use, the xyz basis, I know how the operator y operates on that basis. And the effect of that basis is to introduce the number y, which is the coordinate along the y direction. Okay, so this is a number, so that number certainly commute with the operator t. So I can certainly write this, and the operator t along the I direction translate the first component of the ket xyz that I have from the identity operator, so I end up with this thing here. And of course now we start to see what's going on, because we can replace that equation by something like this, since I can now suppose that I obtain the previous equality from first translating along x and then getting the information along y. In other words, the translation along x and the position operator along y commute. Again, this is not an earth-shattering result, but I think what is really interesting on this slide is that you can learn how to use the identity operator in 3 dimensions. So we find this, that the position along y and the translation along x, they do commute. And of course we can show the same thing for any other combination x, y, and z of the 2 operators, so long as the 2 operators operate along a different direction. So of course that translates directly into the px, since translation can be used, we can use a generator of translation, and we find that y px is equal to 0. So at the end of the day, we can summarize everything by this relationship in the red box, that the I component of the position operator is going to commute with the j component of the p operator, okay, unless I and j are the same. So, for example, if I equal 1, that will be between x and px, and so on and so forth. Here we use I and j in this is to make it general. In that case, so if the 2 components are along the same direction, then the commutator is IH bar. So this is very good, right? This is very interesting. We have a very important commutation, a very important set of commutation relationship. In fact, we have 9 of them, right? 3 times 3, that are going to come very handy for the rest of what we try to do in this chapter. Okay, now let's try to move to a different space. We have this operator Px, Py, Pz. These operators are Hermitian. You know, every generator of a unitary transformation is Hermitian. So I can certainly write now an eigenvalue problem for Px, Py, Pz. And in other words, I can certainly come up with basis state that can be labeled as Px, Py, Pz. And this is what's in the box right here. And the shorthand notation would be to write a vector P. So remember that vector is an eigenstate of the operator Px, Py, and Pz. This is what it means. In fact, it's written right here. The first line there, the eigenvalue problem, says that operating the operator Px on that particular state will return a number Px, and so on and so forth. Okay. We have the orthonormalization property, obviously, that 2p bracket p prime p will be equal to the Dirac delta function, just the same we did for x, y, and z. And finally, we have the, I didn't write here the completeness relationship, but we have a completeness relationship which translates into the probability density, which is the square of the modulus, and therefore the probability, which is the volume element in the p space times the probability density of finding the state in a certain given momentum state Px, Py, Pz, which is written in shorthand as vector P. So everything starts to make sense. There is nothing really new in this. We are essentially generalizing everything to 3 dimensions. Now, the next question we can ask is that now that we have the state P in 3 dimensions, we have the state R in 3 dimensions as well. The question is, how can we represent those states? It is pretty trivial to show the result in the red box. Remember that the x representation of Px is h bar over I, first derivative of dx. First derivative with respect to x of the state. So in 3 dimensions, this is essentially a vector notation here. On the left-hand side, we have a vector coming from P, and on the right-hand side, we have a vector coming from the gradient. So clearly, the R representation of P in 3 dimensions is h bar over I times the gradient vector of R psi. Okay, so that one is actually fairly straightforward. But what about the real space representation of a P state? So suppose that the state is psi is equal to P. Then we can easily calculate our representation of P simply by remembering that each component given between the 3 parentheses there is the complex exponential divided by square root 2 pi h bar. That's what we've done in chapter 6. So now that we know that Px, Py, and Pz, there's no problem with commutation here since these are just numbers, we can put everything back together, and we find that the bracket Rp is given by I PR over h bar divided by 2 pi h bar to the power 3/2. So this is simply a generalization of what we've done in 1 dimension, and this is something you've seen before. Again, this is the kernel you would use in a Fourier transform in 3 dimensions. A Fourier transform might not have the h bar there, but physicists use the h bar, and the h bar is okay because it's done there for normalization, since there is a h bar coming in the argument of the exponential as well. Now that we have set the stage for translation operators and position operators in 3D, let's see a little bit what it means the translation invariance can mean in terms of conservation of linear momentum. So we have translation, we have generators, which is the linear momentum. So let's see how we can connect the two in a formal way. So for that, before we move on, let's just describe a Hamiltonian of an object. So remember, the Hamiltonian is the time evolution, is the generator of the time evolution operator. And we have two bodies, so this is what we're interested in. So the two bodies means that the total Hamiltonian will be given by the kinetic energy of body number 1, which is P1 squared over 2m1, the kinetic energy of the second particle. And then we have a potential that only depends on the distance between the two particles. This is the starting point that we have here. Now, P1 is the three-dimensional momentum operator for particle 1, and we have the same thing for particle 2. Okay, so we have total, we have 6 components: P1x, P1y, P1z, P2x, P2y, P2z. Okay, so same for R1 and R2. So we have lots of operators that are involved. In fact, in the equation of the Hamiltonian, we have essentially 12 operators, right? The 3 components of P1 and P2, and the 3 components of R1 and R2. Now, we are going to introduce a new notation. I mean, it's not really a new notation, but it's a longer notation, which is the notation there, R1, R2, which actually has 6 components, 6 labels. It has 3 labels for particle 1, and it has 3 labels for particle 2. And this is something we've already encountered before in chapter 5 when we were talking about combination of different spins. Here we are going to have a direct product between the position, the 3-dimensional position of particle 1 and the 3-dimensional position of particle 2. This is what the direct product there means. So the cross sign that with a circle around it. So that means that we can combine those components together. So we have 2 Hilbert space for each, 1 Hilbert space for each particle. So those 2 Hilbert space can be combined by this direct product. I think it's important to introduce it this way because the operators we are going to introduce can only operate on individual particles most of the time. I mean, we will introduce operators that operate on both particles as well, but many of the operators like P1, P2, R1, R2 only operates in one given space. So let's see how we go from here. Okay. All right, so this is a bit busy, but let's try to understand what we do. So the first line there that I have under the title translation operator is a translation T1. So it's a translation operator that only operates on particle 1. And we know how we can write this. We can write this with the complex exponential. And it's going to move the position 1 by a vector A. Likewise, for particle 2, we can also translate the particle 2 in 3 dimensions by a value of A. And again, we can use the complex exponential, as we've seen earlier in this screencast, and we can also, of course, use the definition of translation. So what matters here is that T1 operates only on the space of R1 and T2 only operates on the space of R2. I think the notations and the use of indices should make things fairly simple here. So nothing crazy. We just translate one particle along A. We translate the other particle along A as well. We clearly see, we clearly show here that, of course, the 2 operators commute. Why? So the 2 operators, for one operator on P1 and an operator on P2 commute, what clearly shows it is actually a direct product. It simply says that one operator operates on one particle, the other operator operates on another particle. So clearly the order at which we do it does not matter, since we are completely operating, in fact, in different subspaces. So this is all good. So P1, P2 do commute. Now, let's try to move a little bit from here. We are going to calculate the effect of applying T1, T2. So T2 followed by T1 is the same thing as applying the complex exponential. And we can actually put the 2 complex exponential together, the argument together, because P1 and P2 commute. Again, I insist with the red box there that you can only write the second equality because P1 and P2 commute. If they did not commute, you would have the exponential of a commutator showing up somewhere, as we've done before. In any case, the last equality, is a definition of a capital P, which is a total momentum operator, which is P1 plus P2. So I like to insist again here that it can be a little bit confusing to write P1 plus P2 because really P1 operates in one subspace, P2 operates on another subspace. But the same way as we calculated the total spin momentum earlier in chapter 5, we can here combine P1 and P2 through a direct product with an identity operator. So in any case, we get an operator P, capital P, which is P1 plus P2. Okay, so so now it turns out that if I do translate both particles by a value of A, clearly, since the potential only depends on the distance between the particles, we should have a commutation, we should have an invariance of the Hamiltonian with respect to the translation along A for both particles, clearly, right? So, in other words, mathematically, this invariance is translated through the fact that the Hamiltonian should commute with the capital P operator. Right? That's what it means. It means that it doesn't matter. It doesn't matter if I translate or not because we have an invariance. So let's try to see that mathematically. Okay, so let's take a state in general, a general state psi, which is a two-body state vector, and so I can write it on the basis which is obtained from the direct product of the basis R1 and the basis R2. Okay. So in fact, those integral sign is 6 integral sign over all the components of R1 and all the components of R2. And let's try to calculate this operator, this product of 3 operators. So the one operator is the potential operator, which only depends on the distance between the two. And then it's followed by translation of particle 2, and then followed by translation of particle 1. And this is clearly equal to this, right? The difference is being that the operator R1 and R2 have been replaced by the numbers R1 and R2 is actually the vectors R1 and R2, because that operator operates on an eigenstate of R1 and R2. Okay, so far so good. Translating over A, the T2 operator does not operate on V. V is a number, is a function, but it operates on R1, R2, and T1, same thing. So in other words, what I do there, I obtain a V of R1 minus R2 times R1 plus A, R2 plus A. Of course, now we see where we are going with this. We can certainly write this. This is the most important line in the whole proof, because since the potential only depends on the distance between the two particles, now since we have R1 plus A and R2 plus A, this is equivalent to R1 minus R2. Right, since the A would cancel. And of course, that means that we can again reintroduce T1 and T2. So we have just demonstrated that V commute, the V operator, commute with T1's times T2. And by the way, the most important step here was this step that the fact that if we have an operator that only depends on the distance between the two particles, I mean it's not the distance, is the vector connecting the two particles really. We have that equality which was used to write the third equality there in the middle of the slide. Okay, so the point is that the potential operator V of a two-body operator that only depends on the distance between them commute with T1, T2, the product T1, T2. That's what really matters in the box right there. It's a very important result, actually. Let's move on. So we have this result. We obviously also have this result that T1, T2 also commute with P1 square plus P1 square over 2m1 plus P2 square over 2m2. And the reason why it does that is because all the components do commute with each other. So that's trivial to prove. Okay, so now we are in position to write this, because the Hamiltonian is, of course, P1 square over 2m1 plus P2 square over 2m2 plus V of the absolute value between R1 minus R2, I mean the distance between R1 and between 1 and 2. So therefore, the Hamiltonian does commute with T1 times T2. But T1, T2 is also the complex exponential of IP times A over h bar, as we've done just in the previous section. That means at the end, and it's a very important result, it's a reason why it's in a red box, the Hamiltonian and the total momentum operator commute, which is equivalent to saying that the Hamiltonian is invariant for a translation of the system. So if I fully translate my system completely, which is what the P does, capital P is a generator of the total translation, then we have a commutator between them. Of course, we can go back to the time evolution that we've done early in this course and remember that the time derivative of an expectation value of any operator that does not explicitly depend on time is given by I over h bar times the expectation value of the commutator between that operator and the Hamiltonian. Of course, we know HP, we just demonstrated, we just proved that the commutator between H and P is 0. Therefore, we find that dP over dt equals 0. In other words, the expectation value of the linear momentum operator is an invariant of motion, is a constant of motion. There's a reason why this is the invariance. Again, this is another way to say that the system is invariant under a translation of the entire system. Well, this is a conservation law, again, as we have already discovered before. Okay, so let's keep moving now. We have established quite a few commutation relationships. We have realized that the total linear momentum operator P commute with the Hamiltonian if we have for translation invariance. Now let's try to go a little bit deeper to try to understand our two-body problem that we are trying to solve here. And for that, we are going to use the usual thing that you've done in other courses like introductory physics or theoretical mechanics. And we are going to work in the relative and center of mass coordinates. That will allow us to find another number of conservation law and separate the problem into an equivalent one-body problem, really, for a problem, as long as we work in the right coordinates. Okay, let's before we go there, let's try to prove all these things. So we are going to make a change of variables, which will be for mathematical convenience. So first of all, we are going to talk about relative position R1 minus R2. So that will essentially say that the origin of the coordinates will follow one of the two particles. That would be the relative position there, right? And we're also going to talk about the center of mass position, which is, again, just the average between the two positions, which is weighted by the mass of each particle. Again, this is a very typical thing we do each time we try to solve a two-body problem. Nothing really new. Of course, the first thing that you should think about as a quantum physicist is to think about the commutation relation. And the commutation relations that we have is that the position and the total momentum should certainly all commute, that we know. So let's try to see what it means in terms of the relative position and center of mass. So for the center of mass, actually the position, so which we write here as a capital letter X, and the momentum operator are going to obey exactly the same relationship as they did for a normal particle. So we can consider the center of mass as a particle, if you will, if you want, and the commutation relation between the position of the center of mass and its linear momentum will be given by the usual relationship, which is IH bar delta IJ for the Kronecker delta. So if the two directions are the same, we do not have commutation, and if they are not the same, we have a 0 for the commutator. And then we can introduce now the relative momentum operator, which is obtained again by weighted subtraction between the two momentum, weighted by the masses. And when we do that, we can prove very easily again that the position, if we look at the position xi between xi and pj, we find that also we have ih bar delta ij. And again, xi in this case represent the position, the coordinates of the relative position that was introduced on the top left of this slide. So we have all those properties between the total momentum and also the position, the relative position, and the center of mass position. That's what we end up with. So these particular two relationships that we have indicate that the relative position and the center of mass operators commute with each other. That's what we have here. So that's a very interesting thing. So basically what it means is that we can completely separate the positions, the relative position, and the center of mass properties. That's what it means. This is what those two equations mean. So we can solve both problems separately and find eigenstate of the entire problem, which will be eigenstate of both type of operators at the same time. So in other words, if we use a new basis, which is given again by two labels, lowercase r and uppercase r, one being for the relative position, the other one for the position of the center of mass, we can certainly use that. It's perfectly fine. It will make our life easier because we will be able to do a separation of variables between r and r for the reason I gave you. So let's try to see a little bit that in detail. The commutation relationship clearly indicate that this is true, but let's see what it means really in practice. So let's look at the total Hamiltonian. Now we can rewrite the total Hamiltonian as being the kinetic energy of the center of mass plus the kinetic energy of the relative motion. I actually, if you don't see this, I invite you to try to do it by substituting what we came up with, the definition of big P and small p that were provided in the previous slides that we've done so far. Of course, the potential part is easy to get because the potential was only depending on R1 minus R2, which is equivalent to R in our new notations. So we end up with a new Hamiltonian. And of course, we clearly see now why we said that we can separate the variables, because we just have a kinetic term for the center of mass. So it's like a free particle. There's no potential really that's operating on the center of mass. And then the rest is just a one body problem with a kinetic energy of one body plus a potential energy of one body. Here, the one body is this relative motion between the two particles. Okay, so we have the center of mass, we have the relative positions. So we can solve that Hamiltonian, and we can certainly solve the two Hamiltonians separately. And the total energy of the system will simply be the sum of the energy for the center of mass plus the energy for the relative motion. And more importantly, the eigenstate will be obtained by separately by getting the eigenstate for the center of mass, eigenstate of the relative motion, and just by a product between the two, just like we always do when we do separation of variables. Okay, so first of all, let's focus on the center of mass. The Hamiltonian is as simple as it gets. It's a free particle. There is no potential, and we know that for the free particle, for the p operator, actually we can look at this both ways. So let's first do it one way. For the p operator, we know the eigenstates. The eigenstates are written as the ket p. Okay, that means that the eigenstate of the Hamiltonian are also those eigenstate p, since the Hamiltonian is just p squared, right? So the R representation of p is well known. We've done it also a little bit earlier in this screencast, which is just a complex exponential that's obtained there. And this is not very surprising that the representation is this wave, this lack of, because we have a free particle. A free particle, of course, a solution of free particle is a wave that's oscillating like this without any modification to it. So that's a trivial thing to do, okay? This is a trivial thing to calculate, and we are not going to really bother too much with it because it is essentially solved. This is what we solve here. And the kinetic energy will be obtained by p squared over 2m, where p is a number which is the eigenvalue corresponding to the operator p applied to the particular eigenstate p. Okay. So if we suppose that we follow the center of mass frame, we will find that the p can be considered as equal to 0, and we can always do that, especially in this type of dynamics that we are trying to describe things. And we end up with a new Hamiltonian that's just p squared over 2 mu plus v of r. So here the idea is that we are following, we are putting the center of mass at the origin of the coordinates. Okay, so all this work just to show you that the two-body problem for a potential that only depends on the distance between the two particles can be written really as a one-body problem, p squared over 2 mu plus v of r. So we have a single body system in the central potential. So before we move on, let's open a little parenthesis. Can we actually estimate the ground state energy using the uncertainty principle? Because remember, the quantum mechanics will kick in, and it will kick in by the fact that in the previous Hamiltonian, and I'm going to come back here, the Hamiltonian in the box there, we have a p operator and a function of an operator r, and we know that p and r do not commute. So clearly that means that we are going to have this uncertainty relationship that will stem from the commutator that's not equal to 0 between p and r, will have impact on the total energy, on the energy expectation corresponding to the Hamiltonian. So let's try to see a back of the envelope approximation, estimation of what the energy would be. So the Hamiltonian is this. For example, for the hydrogen atom, so this is an example of a two-body potential that only depends on the distance between the two particles. And we are going to be interested in the expectation value of the Hamiltonian, and we are going to call it E1 for the ground state. I mean, that doesn't really matter. We could call it anything we want, but we are going to call it E1 for now. The reason why will become clear later. Okay, so the first term, of course, is that if A is a characteristic size of the atom, in other words, the characteristic distance between the nucleus and the electron in hydrogen, let's say it's A, the expectation value will essentially be E squared over A, where A is a characteristic size. Of course, we do not know the size precisely. There is an uncertainty, but this is essentially what we know about this. Okay, what about the kinetic energy? The kinetic energy, of course, from Heisenberg principle, we know that the uncertainty on the momentum will be larger or equal to h bar over a. Why? Because we know that the uncertainty over the position is at most a, or is around a, right? Or we can say it's a over 2. It doesn't really matter. Let's say it's going to be a over 2, so that the absolute value of the uncertainty on the momentum due to the uncertainty principle would be larger or equal to h bar over a. Okay? Now, here is the next term that we need to do. We are interested in the expectation value of the square of p over 2 mu. This is the kinetic energy. So this is the uncertainty on the kinetic energy. We know, and this is going to be the first equality on that equation there on the bottom of the slide, that part is equal to the uncertainty on p square plus the square of the expectation value of p over 2 mu. We also know that the expectation value of the momentum is going to be 0. There is no reason why not, and we're going to talk about that a little bit later. So in other words, the expectation value of the square of the momentum will be the square of the uncertainty over 2 mu. Of course, yeah, so that's what we have here, is that the expectation value p comes from the fact that it comes from the fact that there is no net momentum on the particle. So we will discuss this later when we talk about the hydrogen atom in more detail. But the point remains that thanks to this, we know now that the energy E1 should be larger or equal to delta P square over 2 mu minus E square over A. So in other words, should be about equal to the value that we have here. Now, what is nice is that if we find that if A decreases, the potential energy potential energy will also decrease, but the kinetic energy will increase. So if you try to bring the electron too close to the momentum to the proton, the potential energy is going to go down. That's nice, but the kinetic energy is going to go high, so higher and higher and higher. In fact, it's going to go higher as 1 over A squared. So clearly there must be an optimal value of A that makes this the most stable. So you want to minimize the kinetic energy and maximize the attraction between the electron and the proton. So how do you do that? Well, you calculate the derivative. You look for the maximum value of E1 for a certain value of A. So in other words, you calculate this. That will give you the maximum of E for a distance A. And this is a trivial derivation, of course. And after you do the derivation of the equation on the black box on the top of the slide, you find that A should be about equal to h bar square over me square, which is actually turns out that with that value of A, you find an energy that goes as me e to the power 4 to 2h bar square. If you suppose that those two equations lead to a length scale of about 1 angstrom and energy about 10 eV. Actually, it should be minus 10 eV, right? So what we see is that this very crude approximation for the energy and for the distance is not bad at all. It's the right order of magnitude, at least. We'll find that the energy is actually minus 13.7. Or actually minus 13.6, and that the distance A should be about 0.5 angstrom for the radius of the hydrogen atom. So, but here we didn't solve any Schrödinger equation or anything. We just solved for the uncertainty principle. So now it appears that we are ready to move on and try to continue analyzing the Schrödinger equation for the two-body problem and see what we can do in terms of rotational invariance. So why do we want to talk about rotational invariance? Well, it's because if we look at this Hamiltonian that we just calculated and we just set up using the relative position and relative momentum P, we found that is indeed that Hamiltonian should be rotationally invariant, since there is no angle dependence on the positions or the relative positions, since all we need is the length of r. So clearly we have a rotational invariance. We also actually have a rotational invariance on p square, because p square being also a distance, it turns out it's a distance in reciprocal space, in momentum space. So clearly we have a rotational invariance in this Hamiltonian, and that should help us a great deal in solving for that Hamiltonian if we know that there is a rotational invariance. And this is what we are going to do now. In fact, I think this is what we are going to do in the next few slides is going to be very enlightening to you about understanding where the rotation how the rotation can apply in quantum mechanics. So let's do it. Well, the first thing we do is we are going to try to rotate a state vector xyz by an infinitesimally small angle d phi around the z-axis. And when we do that, we found what's in the red box. So before you worry about where it's coming from, do not panic. We are going to do that right now. We are going to demonstrate, indeed, that a rotation by an infinitesimally small angle d phi around the z-axis is equivalent to translating by a value of y d phi along the minus y d phi along the x-axis and plus x d phi along the y-axis without touching the z component, obviously, since we are rotating along z. So this is not a quantum mechanical result. This is a geometrical result. So we can prove it the following way. So on the right hand side, the plot I prepared there is a unitary circle, and we have the two position xy and the position x prime y prime. So xy can be identified on the unit circle by the angle theta, and we would like to rotate that the position xy around the z-axis so that we get to x prime y prime, which is just d phi angle further. Okay? So if we start with x prime, we see directly on the plot that x prime is obviously so it's a projection of the point, of the second black point, for the top black point on the x-axis. We see that is the cosine of theta plus d phi, clearly, by definition. You remember we have a unit circle here. Otherwise, we would have to multiply by the radius of the circle. Now, it's very useful to remember basic trigonometry. The cosine a plus b equals cosine a cosine b minus sine a times sine b. That's what we have there. We know that d phi is infinitesimally small, so cos d phi is almost equal to 1. And sine d phi is almost equal to d phi. Then that's what we replace there. And then we also remember that cos theta is exactly the projection of the point xy on the x-axis. In other words, cos theta is x. On the other hand, sine theta is y. This is what we replace, and we end up with x prime be equal to x minus y d phi. You can apply the same kind of logic for the other component y prime. And in fact, I invite you to do it. The result is there on the screen. You just have to use a different trigonometry relationship. The point is, at the end of the day, it shows that rotating by a small angle is the same as translating the two component x and y by the values that are written on the screen. This is the most important point, because now we are going to be able to study what the rotation should be now that we know the translation. Remember, we spent so much time looking at translations in the previous section of this chapter that now we can exploit it even to understand rotation. So we have this result. And we want to be able to write the rotation operator of an infinitesimally small angle by the usual relationship using generators. And here, this is the first time you actually see this version. We used to use Jz or even Sz because the angular momentum we were looking at was spin angular momentum. So this was Sz. And Jz was a general angular momentum. But in this case, I'm using Lz just because we are talking about orbital angular momentum, since we are rotating in space. So we are rotating Cartesian coordinates, really. We are the real space coordinates. Okay, so we are going to try to identify what is Lz. Well, what's nice is this. This ket that I obtain on the left-hand side is obtained by translating the ket xyz by x d phi along y and by minus y d phi along x. But we know exactly what this is because these translations are infinitesimally small, since we have a d phi variable there in each case. So we know exactly how to do this. In fact, this is what is written there. We use a generator of translations. Now we can, of course, multiply these two and also realize that, okay, this is what I just mentioned, translation along x and translation along y. And we obtain this result here. And how can we obtain the result? Well, we obtain the result that comes from the fact, of course, we drop the d phi square term because it vanishes for infinitesimally small d phi. And you see the difference between the previous line and the last line there on the screen is the fact that we can move. We can introduce the operator x and the operator y. I think by now this is pretty straightforward for you to know how to do this. Okay? And this is very interesting because now that we have this, we can identify what Lz is if we remember the other equation that we have in this slide as well. In fact, Lz should be xpy minus ypx. I think that if you remember your cross product or your outer product, that's exactly the component of the angular momentum, even in classical physics. In fact, this is what we have here. In other words, this is the usual definition that you studied in introductory physics for the angular momentum. So that definition still applies when we use operators in quantum mechanics. This is what we have just proven using just 2 slides and a little bit of trigonometry. So I think this is very interesting. So now we can move on from here, and we use L, as I mentioned before, because we rotate coordinates and rather than spin. If we were talking about spin, we would have an S, but then there wouldn't be an equivalent R cross P, obviously, because spin angular momentum does not have a classical equivalent. So let's move on with this. So how do we establish rotational invariance? But by now you know we are going to establish rotational invariance by calculating a commutator and show that the commutator is 0. And which commutator should that be? Well, we are going to use the Hamiltonian. Remember, the Hamiltonian is the generator of time evolution. So this is where the invariance takes into account, comes into the game. And rotational, well, we have the generator of rotation, which is the L, which is the angular momentum, the orbital angular momentum. So in other words, we are going to calculate the commutator between H and L and show that this is equal to 0. And this will establish the rotational invariance of the Hamiltonian I have. Okay, so let's do it. Well, this is a little bit of a busy slide, but let's not get too worried about that. So let's focus on the first line. So let's first calculate the different commutator between the different operators that come into the Hamiltonian. So LZPX is simply going to be calculated by substituting the value of LZ, which is XPY minus YPX. And again, we are going to use the usual commutator relationship that we've seen so many times, and taking into account that PX commutes with PX. And when everything is said and done, we find that the result is I H bar PY. This is for the commutation between LZ and PX. And we can repeat this for the different component. In particular, for the LZ-PZ, we find that those two that commutator is 0. So those two operators do commute. This makes some sense if you think about it, because rotating around Z or translating around Z can be done in any order, as long as we use the Z-axis. We translate along the Z-axis, but you don't need to understand the intuitive result. You can just calculate it, and you very quickly find it is equal to 0. That means now we can calculate the commutator between LZ and P square, because P square is what comes in the Hamiltonian. Remember, this is the kinetic energy, P square over 2m. And we calculate LZ with the commutator between LZ and Px square plus Py square plus Pz square. And of course, we just calculated all the components of this. And what happens is that once you develop that commutator, you find that it's actually equal to 0. So in other words, LZ and P square is equal to 0. Good. We are halfway there. This is just what we can also show, of course, that we are halfway there. And the second half we should show is that LZ does also commute with x square plus y square plus z square. And this is a very good exercise for you to do to get the commutators simply by replacing LZ by xpy minus ypx. And then you calculate exactly the same way as we calculated the other 3 commutators that are on the top left of this slide. So when we're done, we find that LZ commute with p square, LZ commute with r square. Therefore, the Hamiltonian and LZ commute. So this is what we mean by rotational invariance of the Hamiltonian. Again, extremely important result, because that means that we can find a set of eigenstates that diagonalize both H and LZ at the same time. And this is, of course, a very important thing, and it's the reason why we can label some of the eigenstate of a central potential problem, like, for example, the hydrogen atom. This is where the LZ come. You remember the S state, P state, D state, and so on. And we are going to study that later. They come exactly from there. They come exactly from the fact that they are good quantum numbers. In other words, they do describe a state of both LZ and the Hamiltonian. I'm kind of jumping the guns a little bit. We'll see that later. Now, we can also use spherical coordinates instead of Cartesian coordinates. If I have a spherically spherical symmetry, I usually use spherical coordinates. And again, by now you know how that works for the ket. We just use r, theta, and phi as parameter. And rotating that particular ket, r, theta, phi, is very straightforward. Of course, we just modify one of the angle of the spherical coordinates. And we can then calculate the commutator between r and the potential, and this is obtained again because we know how v that only depends on the length r operates. That's what we have on the on the right hand side of the first equality. And of course we can rotate, we can commute things around. This is kind of a calculation that we've done many times before, but this is good to be reminded, and maybe to stop the screencast and take a piece of paper and do it for yourself if you're not convinced. And then that shows simply that we have a space that's isotropic. In other words, it doesn't matter how much we rotate the system, the potential is still the same, which makes sense. It's spherically symmetric, of course. That means that we don't see which direction we are. We could rotate the thing any angle, it would not change the potential whatsoever. Okay, so we can repeat all the calculations for the rotational around x, around z, along y. We can do all that, and if we have an invariance in the 3-dimension, we find that we have indeed HLX, HLY, and HLZ. Now, the big question I have for you before we move forward is, of course, does that mean I can pick eigenstates that are common to H, Ly, Lx, Ly, and Lz at the same time? Well, this is a very important question to ponder. But remember, Lx, Ly, Lz are the component of an angular momentum. And an angular momentum is described by the commutator relationship between its components, which are not zero. So Lx, Ly, Lx, Lz, or Ly, Lz do not commute. So I will never be able to find a common set of eigenvalues, of eigenstates that diagonalize H, Lx, Ly, Lz at the same time. Instead, these three equations that I have on the slide, they do establish one thing. I could pick a set of eigenstates that diagonalize H and Lx at the same time, yes. Or I could use a set of eigenstates that diagonalize H and Ly at the same time. Or I could use a set of eigenstates that diagonalize H and Lz at the same time, but not all at the same time. No, not all four. Okay. So that only says that the system is invariant around any axis, or the angular momentum is conserved. Okay, so let's continue. And now we are going to study the importance of finding a number of observables, so those operators that are Hermitian, that commute between each other and therefore can be used to simultaneously diagonalize the Hamiltonian. So we know, of course, that certainly we cannot use more than one component of the angular momentum operator L with component Lx, Ly, Lz. We cannot do that simply because we know that the important definition, what part of the definition of an angular momentum is those three commutation relationships that are here on the slide. Clearly that means that you cannot diagonalize Lx and Ly at the same time, or Lx and Lz at the same time, or Ly and Lz at the same time. So we know that. Okay? So in order to try to move a little bit forward and to make the mathematics a little bit more bearable, we are going to introduce what's known the antisymmetric tensor epsilon ijk, so that we can actually write all those relationships, those commutation relationships, in a very synthetic way, very small, very shorthand way. So what we introduce is what's known as the Levi-Civita symbol. Levi-Civita symbol. It's it's a tensor that has 3 indices, I, j, and k. And basically, it's going to be 0 if any two of the indices are equal. It's going to be 1 if the indices are in a normal normal order, like 1, 2, 3, for example, or 2, 3, 1, or 3, 1, 2, as shown on the cycle in yellow. And will be -1 if the permutation is the other direction, so it's clockwise on this graph. So 1, 3, 2, 2, 1, 3, 1, 3, 2, and 3, 2, 1. Otherwise, it is 0. So if you use that, that allows you to actually write those commutator relationship as in a single way, as written in this red box. So that allows us to write everything properly. So you see what it means is that we will be able to do some algebra thanks to this. And in fact, you will do that in the homework and even in the in-class activities. We are going to work on that. So we have those 3 commutator relationship. And we can, that means, as I said a minute ago, that we cannot use more than one component of L to diagonalize H. Because if we did, we could not find a common set of eigenvector of those two operators. On the other hand, now, L square, which is Lx squared plus Ly squared plus Lz squared, does commute with the Hamiltonian. Therefore, we can pick this full set of operators that commute, H, Lz, and L square. We could also use H, Lx, and L square, or we could use H, Ly, and L square. But these are the only possible combination we can use. So, of course, what this allows me to do is to use the labels E, L, and M that corresponds to the eigenvalues of H, L square, and Lz. So we know that the eigenvalue of H is a number E. It corresponds to the energy of the system. The eigenvalue of L square is L times L plus 1 times H bar square. Therefore, we can use the label L to uniquely define what is an eigenvalue of L square. And for Lz, the eigenvalues are mh bar, with m taking values between minus L and plus L. So we can label, therefore, all the eigenstates that are common eigenstate to H, L square, and Lz with the labels E, L, and M. So now we are going to rewrite the Hamiltonian, and we are going to rewrite it with a little bit of tedious mathematics that is going to take a few minutes to do. In fact, it's going to be a part of an exercise. It's part of the problems at the end of the chapter, which will be suggested as a homework for those who are following this course in the regular semester. In fact, the fact is L square, as we know, L is R cross P in commutator, using commutators. So L square is R cross P dot R cross P. We can show that it's equal to R square P square minus R dot P square plus IH bar R dot P. This relationship is not trivial. I mean, it takes quite a bit of work to get there. This is not obvious we get there. So this takes a little bit of time that I'm not going to spend on this screencast, but this is going to be part of an exercise to perform. The difficulty here is that we cannot use the formula we know from vector analysis, because R and P are here operators and not just simple vectors, and those operators do not commute. So that's a difficulty. Anyways, the reason why I do this is because now that means that the R representation of the effect of L square on a state psi can be written by substitution from the first equation. And when I do that, I find something that's very interesting. So that's what is on the right-hand side. We are going to look at the 3 different components of the equation. The first component is simply given by remembering that
operator R is Hermitian and can operate equally on the left or on the right in a bracket. So in this case, it's going to operate on the left, and it's going to give me the number R square. And that will be, and the rest is there because we don't know how P square is going to apply on psi, but that's okay because that will allow us to highlight the presence of R square times the R representation of what the operator P square does on state psi. And here you start to see why it's important, because P square is really giving the kinetic energy of the problem. So before we go there, let's continue. R dot P, we can use the same trick that R operates on the left on the eigenstate R. So R can come out. At the same time, we also know that the R representation of the operator P on a state psi is the gradient. H bar over I times the gradient. Since we work in spherical coordinates, this is going to be exactly equal and to h bar over I, R times the partial derivative of the wave function with respect to the radius R. This comes from the fact, of course, that I have a dot between R and P. And finally, the last part, the third line, will come from the fact that the operator R dot P square is the application of the operator R dot P twice. So we can use what we have on the previous line, and we do not multiply. Obviously, we apply twice. So that's what you see. There's a reason why there is a R times the partial derivative with respect to R in parentheses. So now we can put all this together on the left-hand side, and that allows me to write, by rearranging the terms, allows me to write that the kinetic, the part of represented the kinetic energy, so the R representation of what the kinetic energy operators does on the state psi, we can write it now in terms of the derivative with respect to R plus the R representation of what the angular momentum operator L square does on psi. If here, in fact, it's a specific angular momentum, it's an orbital angular momentum, it is related to actually a movement in space. We start to see a little bit how we're going with this, because that will allow me to rewrite the Hamiltonian. Remember, the Schrödinger equation, it's written on the left-hand side, is the kinetic energy plus the potential energy. Here we write it in the R representation. Now I can replace the P square over 2 mu by what I just calculated, and that gives me a Schrödinger equation in this state. So you see how we work here. This is a little bit tedious to get here, but it's very logical. I mean, there's no step is really crazy. We just have to be able to write the first equation up there, which is the only thing that's not trivial. Okay, let's try to move on from here. So this is the equation we just did. And this piece here, I would like you to remember, the first two parts of this equation come from the kinetic energy. In fact, the second part, which I point in green, is also part of the kinetic energy, but it's related, if you remember your course in classical mechanics, it's actually related to the rotational kinetic energy. It looks like L square over I, right? I being, actually over 2I, I being the moment of inertia. So it's really a kinetic energy, really. And the other part on the left-hand side is, of course, the radial part. Now, we can see why it's the radial part if we defined a PR by h bar over I derivative with respect to R plus 1 over R. If we do that, we find that indeed PR square over 2m, which is the kinetic energy related to the radial component of the linear momentum, is indeed equal to the part that's on the left-hand side of the Schrödinger equation up there. So this is all makes sense, and of course the PR we get there goes from differential analysis that we've done before. Okay, so we have this equation, so we are moving very well forward. Let's try to do what we can do. Now, we suppose that we are going to use a state that is a simultaneous eigenset of H, L square, and Lz. And we understand now why we try to highlight the presence of L square. Because if we use a state that's an eigenstate of L square, this equation is going to be simplified significantly. Indeed, we know what L square does on the particular state ELN. So how I got from the top equation to the second equation is by applying the equation not so much in the general state psi, but instead of a state ELM, which is an eigenstate of H, L square, and Lz. There's a reason why I can replace the rotational kinetic energy by L times L plus 1 H bar square over 2 mu R square. Okay, so this is great. We actually made a lot of progress just here. We can of course write the wave function, so the R representation of the state ELM. We can separate into the R component, a theta component, and a phi component, because we see that the terms are separable. So we can certainly write that without a problem. And once we do that, we find that the only piece that remains for the radial part is one equation that only depends on the radius. And this is the equation that we have to find to compute the radial part. So what's important here, of course, is to notice that there is no m dependence in that equation. That simply means that the energy, which can be labeled with an L and an M, that energy will be degenerate for m, since clearly the equation does not depend on m. So if I use different values of m, I will get the same energy, clearly, since there is no dependence. So this is already a degeneracy that we are going to measure. Okay, so, and it's related, of course, to the spherical coordinates, the spherical symmetry, sorry, and the lack of a preferred axis. So we see that we actually end up with a one-dimensional problem with R. And we can even make it simpler, in fact. We can make it simpler by notice that we can write the radial part as being some function u of R divided by R. That doesn't really make any difference because we don't know what u of R is. So this is not a simplification in principle. But what it does, it actually simplifies the equation, because if I plug in u R divided by R in the top equation, I find that I end up with this the Schrödinger equation that looks it's actually much more simple, because we have cancellation of the first derivatives that comes from the derivatives by part, I mean the chain rule, and we end up with something that looks very much like a one-dimensional Schrödinger equation. And this is something already here that I like to attract your attention on, is that we have an effective potential, V effective of R. That's V of R, of course, that's the external potential that we had since the beginning, plus a term that looks like a potential term, L times L plus 1 H bar square over 2 mu R square. But we know better, of course. That term is really a kinetic energy that comes from the fact that we have a rotational kinetic energy. However, for all practical and mathematical purposes, this term looks like a potential energy. In fact, this is what you have probably encountered in your earlier classes as the centrifugal barrier. This is a potential that's try to bring the particle as far away from the center as possible, and this is true as the larger the L, the farther away the farther on the right, the farther for large value of R, the potential will bring the particle into. So this is essentially how we solve this problem right here. There will be no centrifugal force for L equals 0. And in fact, if L equals 0, which is an S state, we will find that there is no centrifugal force. In other words, the, let's say, electron will actually be the case where the electron will be the closer to the proton. And this is, of course, in the case of the hydrogen atom. So before we continue and to different consideration for the spherically symmetric system, I'd like to say a word about the cylindrical system, and it's the example 9.1 in your book. If you have a system that has the full symmetry of a cylinder, the right operators to use now are no longer Lz and L square, because we don't know anything about Lx and Ly clearly. So the symmetries we have is the translation along the cylinder, so that the generator of which being Pz, and the rotation around Z, so the generator of which is Lz. So now the three operators that we need to use in that case would be H, Lz, and Pz. So this is an example of the fact that to find the complete set of commuting observable for a given system depend on the symmetry. So this is a beautiful example on a cylinder that you would use a different symmetry. So H, Lz, and Pz will actually be the right quantum number. So it's very interesting to notice that in that case, Pz would be actually Pz would commute with H. So that makes things a little bit easier to calculate the kinetic energy, for instance, along at least the kinetic energy along the z-axis. In any case, this is an example for cylindrical coordinates, cylindrical symmetry. So now I'd like to move on a little bit and try to talk a little bit about the position space representation of all the operators we've been talking about, and that will allow us to come up with a representation of the eigenstate of H, Lz, and L square for everything that we have been looking at. So we are working in spherical coordinates, and we have already established in the previous section that we need to solve the Schrödinger equation for the radial part in order to have the radial part of the solution. Now, what's interesting to do, though, is to look a little bit what happens in the angular parts, so for theta and phi, so the azimuthal and the orbital angle that we are talking about. So remember, before we move too far, we are going to remember that the rotation around the z-axis in spherical coordinates can be written using the r theta phi notation, and we use that because the rotation of an angle d phi is, of course, obviously given by just shifting the phi angle. We can try to do the same for the adjoint part. So of course the adjoint part, as we know, it operates exactly the same way on a bra than the non-adjoint part operates on a ket. So this is by definition, of course, this line that I put there. Now, what we can do, we can calculate also what's the effect of the rotation, not the adjoint, but the rotation, what's the effect on the left-hand side. Well, since the operator r is unitary, a rotation of the adjoint is equal to the inverse of the operator. But the inverse of operator r of angle d phi is a rotation of an angle minus d phi, right? It's the inverse rotation. So that means that the effect of the operator r on the left-hand side is to change the angle by minus d phi. Okay? It comes from the fact that the rotation operator is unitary. Now we can use the Taylor series for the small angle because we work on small angle when that particular construction, this particular bra, is coupled with the ket psi. Okay, so we do that from the previous equation, and we can of course write this Taylor series for small angle. So the first part there is the zero angle, and the second part is the correction due to the fact that we have a small angle at first order. The second order and further and higher orders can be negligible, can be neglected because d phi is infinitesimally small, so the high power of d phi are also even smaller and in fact negligible. So what's nice, of course, is that we have that solution, but we also have this equation. This equation here is just rewriting the rotation of a small angle in terms of the generator of rotation. The generator of rotation, as we have seen, is Lz, Lz being the orbital angular momentum operator. Okay? So that means that we can see from all this, if I compare the different equations, I find that the effect of Lz is actually the representation of Lz in cylindrical coordinates. It's actually the same as multiplying by h over I derivative with respect to d phi, which makes a lot of sense, of course, because Lz is a rotation around the z-axis, which rotates around phi. So we understand exactly the same way as we understand the linear momentum. which the translation around the x-axis is the derivative with respect to x. So you see here, in one case we have a representation in x representation, we have px, which is the derivative, and in spherical coordinates, we find that the representation of Lz, so the generator of rotations, is given by, similarly, by h bar over I times the first derivative with respect to the angle phi. Okay, so this is all good, all nice, because that will allow us now to find what are the eigenvalues and the eigenstate of actually the eigenstate. The eigenvalues we already know what they are, but we will find the eigenstate of Lz now that we know what is its representation in spherical coordinates. It's a very simple representation. So this is what this is, right? The representation of Lz in spherical coordinates is the same as taking the first derivative with respect to d phi times h bar of I. Now, we can take a state, for example, Lm, which we know is an eigenstate of Lz. Yeah, that's exactly this. It's an eigenstate of Lz with eigenvalue mh bar, m taking all the values between minus L and L. So if we do that, we can, of course, remember what is the effect of Lz in spherical coordinates, which is just like I wrote in the box on the top of this slide. And at the same time, this is equal to mh bar times the same function. So here we have a very simple ODE, well actually it's a PDE, but a very simple PDE that says that the derivative of a function is equal to that function times a number. So of course we know what function can do that. This is the exponential being the only function that of which the derivative gives the same function. So we find that the angular dependence of the function, of course, is going to be given by this kind of terms, em dot phi. Okay, so that's all nice, but what we also see, and it's important, is that we expect this function to be periodic. If I change phi by 2 pi, that means that I do a full rotation, and clearly that means that I get the same result. So we see that because of that, the only way that things can work out is that if m is an integer. So in other words, if m is an integer, L is also an integer, which is very different from what we found for spin. For spin, we found that m could be half integer, right? It was when the spin state could pick up a phase of -1 when we rotate it of 2 pi. Here we cannot do that because we're in real space. So we find that there's a big difference between this angular momentum, which is the orbital angular momentum Lz, and the spin angular momentum Sz. The mathematics is very, very similar, but the big difference between the two is that Lz takes, L in the case of the orbital angular momentum can only take integer values, while L in the case, actually S, this is the number S in the case of the spin angular momentum, can take half integer values. Okay, all right. So we can keep going and get the other components of angular momentum, which would be Lx and Ly, and we do that by remembering that the effect of P in Cartesian coordinates is h bar over I times the gradient. Right? This is in Cartesian coordinates in x, y, z representation. So we can write this by going from Cartesian coordinates into spherical coordinates, and this is what this ugly looking equation is about. This is really no big deal. It's just simply saying that we go from, we express everything in spherical coordinates, and that allows us, of course, to write Lx and Ly by taking the x and y component of these equations. This is the kind of equation that we find in tables of formula. This is a differential equation. This is something that's pretty well established. It can be confusing if you don't pay attention to your bookkeeping, but there is really no additional physics coming from the mathematical manipulations that we have to perform to get this. The point is, at the end of the day, we can calculate L square as being Lx square plus Ly square plus Lz square in the spherical coordinates, and this is what we obtain in the red box. So we have all the differential equations we need, and we can start to operate them to find the eigenstate in spherical coordinates. Okay, and this is what we are going to do now. So we are going, now that we know how the operators look like in spherical coordinates, we can find what the eigenfunctions will be. Okay? So first, before we go there, we have to remember that rotating a position eigenstate does not change its length, it changes direction. So that means that we can certainly isolate the angular dependence, and then we have seen already that the angular dependence can be separated. We have seen that so far, actually. This is what we've done by going in a spherically symmetric problem. We find that the Hamiltonian, the Schrödinger equation, does not have a phi and theta dependence. In other words, we can separate the solution for r and solution for r theta. So we do that, and we find spherical harmonics YLM depends on theta and phi. So that means that, and this is a notation really. I mean, this notation, spherical harmonic, is a notation. It's just the LM state in spherical coordinates. That's what it means. It's a notation. This is nothing else. It's a definition, and we can write the full equations now as a spherical harmonics times the radial part that depends on the potential VR. So that one we don't know for everything. But YLM, we do know. It's YLM are the eigenstate of L square and LZ. So we can calculate them in all generality. And this is what we are going to do now. Okay, this is coming from the fact that we have spherically symmetric. So we would like to have those states to be normalized, and because we don't want to lose particles, for sure, and we certainly do not want to create new ones. And we can do that by doing the integral of the volume in 3 dimensions, which is something that we can do in general in spherical coordinates. So if we do that in spherical coordinates, instead of looking at cubes as we would in Cartesian coordinates, now we are looking at a solid angle. So the solid angle is that angle that's an angle in 3 dimensions. That's actually represented by this little section that I show there on the right-hand side with d omega. That's actually this angle that's obtained by sine theta, d theta, d phi. So this is something that we do very often. The solid angle is basically the surface under a certain angle and along another angle in the other direction, and then we just look and then we find the solid angle. So just to give you an example, if you integrate the solid angle d phi for sphere, you find 4 pi, which is the origin of the 4 pi that you have in the surface area for sphere, which is 4 pi r square, or even the 4 pi that shows up in the description of the volume of a sphere, which is 4 pi r cubed over 3. So all that makes sense. So now we have to normalize the wave function and normalize all the states, and this is what we are going to do in using the solid angle. Okay. So the point is we try to normalize the angle separately, and so we want to make sure that the spherical harmonics are properly normalized. That's the main thing. And we do that by integrating over a solid angle d omega. Now that allows me to say this, that the spherical harmonic square times d omega, so the solid angle, will be the probability of finding the particle at angle theta d phi within the solid angle d omega. That's really what it means. So you have to think about this in 3 dimensions. Okay? So how do we find this? Can we find the spherical harmonics? Well, by solving the differential equation. And the best way to do this is to start, I mean, there are many ways to do it, but an easy way to do it is to use the L plus. Remember the raising operator? We cannot raise a maximum value of m, which is L. We cannot do that. I mean, we can, but then we get to 0. That's what the equation in the box says. And of course, L plus is Lx plus ILy. And we know Lx and Ly. We just did it in the previous section of this screencast. So if we know Lx and Ly, we can calculate L plus. In fact, we can calculate L minus as well, and it's the one that's written on the slide here. So in position space now, in other words, by projecting on the bracket theta phi on the left-hand side, we can actually obtain a differential equation that we need to solve. Now, if we do that, And we remember the phi dependence. Remember, we've done that earlier. We know that the phi dependence is EIL phi. We did that a few minutes ago in another slide. We end up with this equation here to solve, which looks like a fairly simple equation to solve, but it's maybe it is not directly trivial to see that the solution for this problem is obtained by a sine theta to the power L. That's what we find by solving this equation, while the EIL phi is the dependence for the angle phi. This is what we obtained for the spherical coordinates representation of the maximum projection state, LL. Now that we have this, of course, we can operate. We will be able to operate and go down by reducing the projection using the L minus. But before that, we can also normalize that state, and we can normalize it the way I explained before, so by integrating over this solid angle. And when everything is said and done, the state looks like this. Now we can get all the other states by applying L minus to all those states, since we can then get L minus one state and so on and so forth, all the way to the minimum state that we can get, which is L minus L. So this is the operation here. They're nothing really difficult. This is something that we do on a piece of paper that's much easier, and this is something that we do by solving the problems at the end of the chapter as well. But when everything is said and done, we get this kind of very ugly looking equation for the spherical harmonics. Actually, a mathematician would say that it's a beautiful equation. I say ugly looking because it's a little bit tedious to solve this problem, but it's exact. So it's an exact equation, so it's exact solution of L square and LZ. I like to remind you that those spherical harmonics, they are the spherical coordinates representation of the eigenstate of L square and LZ. This is a very important result. You might not remember the exact mathematical form, mathematical expression for them, but you certainly should know what they are. And in fact, they are obtained by what's called a Legendre polynomial, which is obtained again by this recursion relationship that you find in most books of formula in physics. They have a number of properties that I'm not going to discuss too much, how we relate the plus m and minus m state. You see here there is a parity effect and the conjugate effect. Of course, the spherical harmonics function are complex functions. And then at the end of the day, you can calculate all of them, and you find that you find a familiar representation between a fully spherical symmetric state, which would be the S state, with L equals 0, M equals 0. Then you get this P state when L equals 1, and it's of course triply degenerated. M equals minus 1, M equals plus 1, and then M equals 0, and so on and so forth. You can do the D state, you can do the F state, and so on and so forth. And they all have a representation of being all eigenstate of LZ. And you see that the eigenstate of LZ, they're all invariant under the effect of LZ. You see that, since LZ is the axis that points to the vertically to the top. So sometimes you have heard about Px, Py, Pz. These are the D states, so the L equal 1 state that are used, for example, as the orbitals for carbon. So what do they look like? Well, it turns out that the Y10 state, so the can be expressed mathematically by the expression here, Z over R, when we remember that Z is nothing else than R cos theta. So this is actually the PZ state. So the PZ state is indeed an eigenstate of LZ and L square. Unfortunately, the other two states, Y1 minus 1 and Y1 plus 1, they are not. they are not state like that. They are not exactly x and y state. In order to get them, we need to actually calculate a superposition of two states. And the way you look at it, and again, this comes from the equation that won the previous slide, is that y11, for example, involve both x and y. And y1 minus 1 also involve x and y. And obviously, the px and py state that we obtain from x over r and y over r can be obtained by linear combination of the y1 minus 1, y11. Okay, so what's important to note here is, of course, px and py are eigenstate of Lx and Ly. So clearly, that makes sense that that the eigenstate of Lz will not be eigenstate of Ly and Lx, since Lz and Lx and Ly do not commute. So in fact, this is exactly what we see here, that y1 minus 1 and y11 are eigenstate of L square and Lz, but their combination, the linear combination, are no longer eigenstate of Lz. Why? Because they correspond to eigenstate of Lz with different eigenvalues. So since they don't degenerate, their combination is no longer an eigenstate of Lz. But they are still eigenstate of L square. And in fact, they are eigenstate of Lx and Ly as well. So it turns out that in this case, it's easier to calculate linear combinations because of the way things look in direct space.